to manually.
Yeah.
Can you tell every time?
Yeah.
Right outside. I don't need ice cream. I exercised this morning.
Make quick. Then you can also say, make me construct.
Also like a euro Okay. Okay, let's get started. Okay. We'll get started.
Hi, everyone. Welcome to AIDC meeting. Becoming a great tradition. We are trying to keep you busy every ATF. So welcome to AIDC at ATF 121. And please, please be familiar with IDF policies, how your contributions are treated by ATF. There's a number of documents that's mentioned here. Our lawyers ask us to read it really slowly. Please be aware of IETF rules and policies.
And the meeting is recorded.
We've got very exciting program for you today. So, you know, we are trying to bring together academia, people who implement, people who use. So today we've got a combination of people who are building really, really large clusters. Adi from Meta is going to talk about how they're building their AI systems. Peter Lepukhov is going to talk about AI technologies networking from vendor perspective, more or less. And then we'll have Jay Kelly from Google talking about what they do in infra engineering at Google. With regards to question, after each presentation, we'll have 5 minutes for QA. Today is a busy day, so 5 minutes, it's kind of tight. We can afford out of 2 hours. So we didn't get any slides from presenters yet. At the moment, the slides are going to be available. We will publish them on the site that you see here. And when we get the recording, it will be shared accordingly on the same place, right?
Yeah,
So Adi, are you there? See.
first one. You can stop share.
Yeah. Nope.
You're still sharing.
Yeah, listen.
Okay.
Okay.
So who is the quick one? You will share the slides or he will share the slides?
We don't have the slides.
Okay. You can share the slides from the WebEx.
Sorry, could you repeat it?
Just 1 minute.
Yes.
No, not yet. 2 more minutes. There's some technical difficulties.
So we will have all the meeting materials, including the recording, later in the GitHub repository. So if from the same account, you can also find the materials and recordings of the previous AIDC set meetings. So, but anyway, if you need any information, you cannot find it, you can always send us an email and we will be happy to provide you a link. And we also have the AIDC mailing list, and you can subscribe to it and send your questions or share information there, make a comments, all welcome.
And 2 more minutes.
So if you have a topic you want to present at the next AIDC meeting, you are also welcome to send us, the topic you want to present, the expected length, and we'll try to see whether we can accommodate you. Okay. There yet.
The topics we are mostly interested in are networking at scale. We quickly went from 8K GPU cluster to 32K to 100K. 100K cluster has been announced already. It's run by XAI, public information, beautiful photos and videos of it. So we are looking forward to either information about how you're working on it, your operational experiences. We're looking forward to problem statements with regards to, there's issues with load balancing, with congestion control, not necessarily issues, but the topic worth discussing, given the scale and the size of the network and amount of data that needs to traverse the network. So we are looking forward to kind of more participation from regular IETF folks, both on the routing side of things. So how do we make routing better, faster, higher fidelity, and so forth, as well as potentially CCWG and transport. Let's see. We always manage to make networks work, but IT stuff is unmanageable.
So if you have a specific question about the latest development in this area, you want to know more information about that, you can also send a question to the list or directly to me and Jeff, and we will try to see whether we can find somebody to present in that area. Okay. Do we have the presenter?
If anyone's got a phone, if it's not, maybe we can have them figure out the Wi-Fi.
I see. Sorry. I see just the list of participants, no presentation and no view of the room. Is it something common or?
The remote presenter has a little bit technical issue, so I'm waiting.
Okay, thank you. Thank you, Ajahn. But because it wasn't, I was a few minutes late and didn't understand what happens. Okay, whatever the reason, of course.
Yeah.
So you said there is a repository for all the presentations that has been made in the AIDC, easily accessible. Is that what I heard?
Absolutely. So all the presentation that has been shared by the presenters are available on the
GitHub
GitHub
repository.
repository that we use for the meeting.
And so it's a
That also
GitHub
includes the
repository.
recordings.
So
And
if
the-
you look at the GitHub repository I sent for this meeting, and we have the chair slides, and there you can, inside that, you can find all the repository information.
And if I didn't get the email, I just found your WebEx link on the public side meetings link on the IETF
Okay.
121. How do I get the
So
GitHub?
how about you send me or Jeff an email later? We'll send you the pointer.
No problem. Thank you very much.
Adi, I made you a presenter, so you can go ahead, share your slides. We cannot hear you.
Now can you all hear me?
Yeah, I can hear you now.
Oh, perfect. Sorry about that. I'm traveling and I messed up the time zone a little, so not my home time zone. Yes. So that, yeah. Can you all see my screen?
Yes, we can see the screen.
Yeah. So I can't see the hands or anything like that. So Jeff, if something's going on, if someone wants to ask a question or anything like that,
Sure.
you can just interrupt with your voice, I think. Yeah. Thank you. Yeah. Thank you. Hi all. I'm Adi Gangiri. I'm a production network engineer at Meta, specifically focusing on AI networking. And my talk today is on network and communication infrastructure powering Meta's Gen AI and recommendation systems. I think I'll roughly go on for like 30 minutes or so, and then we have some Q&A. So in terms of the agenda, I think we have quite a lot to cover, but I'll touch upon some of these topics and quickly move on. We have spoken about some of these topics, but not all of them in the same forum. We did build like a holistic story in the past, so I think this is our attempt to do so. We have spoken at SIGCOM, networking at scale, and a few other forums. I will share those links in these slides as well, just in case if we don't go deep enough into any of these topics. Definitely, we can also discuss it during Q&A, or you can reach me after the talk if you have any more in-depth questions or clarifications needed. So I think, the talk is, I think trying to motivate so as to why in the beginning, building these AI systems, what use cases we're building for. And then we talk about topology routing, we touch upon transport, and performance tuning a little bit in terms of some of the clusters Meta is building, and in terms of like what it took, from taking it from out of box performance to optimal performance, if you will. We'll briefly touch upon distributed inference, which is basically a very emerging direction for which I think, these large, RDMA clusters in general may be needed as well. Distributed inference has some unique use cases, unique traffic patterns and network requirements as well. So we touch upon that and talk about some future considerations. So there are three reasons why we're building, large Gen AI, large clusters for Gen AI or recommendation models, or distributed inference, right? So those are the three reasons why we're building it. The first and foremost reason why we got started building RDMA systems at Meta is because of recommendation models, and specifically recommendation models. When I refer to that, if you think of use cases, when you go to news feed at, on the Facebook app or Instagram app, or when you kind of look at the stories in terms of how they're, ordered, or when you go try and discover something, all the suggestions that you get, all of that essentially is a byproduct of these recommendations models. And specifically, Meta wrote a paper and open sourced some code around deep learning recommendation models, or DLRMs, which have quite interesting properties in terms of their compute footprint and communication footprint. And specifically highlighting on the communication footprint, it has a full mesh like traffic pattern. And even, in terms of like why we had to build a pretty high speed network for training recommendation models, this particular number or insight should give you some good mental model, right? Even after we port these models to run on the fastest RDMA systems of that generation, in terms of like how the models are growing and so on, it still end up about the models being communication bound to about 40 to 60%. This is after we move these models to run on RDMA based clusters, high speed clusters for the state of the art networking in that generation. Typically, the amount of exposed communication, which basically is the amount of time where you're not doing any computation, is about 40 to 60%, right? So the second use case, I think, related to why we're building larger and larger clusters is Gen AI, which everybody's talking about it. We recently open sourced with Llama 3 models. In terms of the foundational models, the 8 billion, 70 billion, and 405 billion parameter models were open source, and the reception's been really warm, as you all may have heard about it. And we are also using these models to build products. Like, for example, when you go to WhatsApp or Instagram or a bunch of other apps and use Meta AI, or Meta AI also has a web version. Essentially, all of these models are backing these use cases, right? And in terms of like why we need bigger and bigger clusters, in general, there's consensus that we've not hit the wall in terms of the dense part of the model. That bigger models result in better predictions, right? So I have this like funny example of asking to generate a really photorealistic pug image, and you can see on the left, the image is very caricaturish in some sense. But as we went on with Llama, the first version of Llama and Llama 2 and Llama 3, the images it generates gets better and better over time, right? In some sense, this corresponds to bigger and bigger infrastructure being able to train larger and larger models on more and more data, right? So that's about training. But now thinking about inference itself, thinking about inference of these Gen AI requests, for example, as these Gen AI use cases come through, the scale of distributed inference is fairly large, right? Because the number of concurrent requests are increasing also. But especially in the case of Gen AI, the inference requests are fairly expensive. And so there is this interesting trade-off where you could train a really, really good model, but in order to like actually serve that model, you also need strong infrastructure, and you also need to serve these requests in limited amount of time, right? Which means that the backend computation for distributed inference needs to be fast enough, right? And we are approaching a scale of these models, and with the amount of accuracy we want to serve them, which is another trade-off, we do need this backend computation to be fast enough, and that requires also distributing model across various servers, even the inference part of the model, right? So which is also resulting in more need for building RDMA systems or GPUs connected with RDMA systems, right? So in summary, these are the three use cases why we're building these RDMA systems for. And in terms of our evolution, so roughly around year 2020, we moved from asynchronous training and CPU-based training to GPU-based training, and pretty much, and also full sync training, meaning at the end of every training iteration, all the processes or that are living on all the GPUs need to synchronize with each other, resulting in essentially higher demand for communication for these training models, specifically recommendation models, which is what we got started with. And then over time, it wasn't like those models kind of stayed as they are. The model complexity, the amount of data we need to train, and hence the scale of needing to train these models also exploded. And then for this, we had to figure out how to parallelize this model across all of these GPUs, right? Because as the amount of GPUs increases, the amount of potential inefficiency also increases, right? And then that essentially what results in a need for a network which is high bandwidth and which can advertise low and predictable latency, right? And in terms of like how we solve these problems, right, we started building RDMA networks. Specifically, they were purpose built for AI workloads, and especially in the beginning, we started deploying with Rocky V2 or RDMA over converged Ethernet, and we use PFC to make sure we can have a lossless network. We have very large deployment, total deployment in terms of like the number of RDMA NICs or GPUs. In this case, this is hundreds of thousands of GPUs on these RDMA clusters, and our cluster size, until recently, we spoke about this large 24K cluster, so it was in tens of thousands of GPUs. But in the Meta Q3 earnings, Mark recently announced about that we are training Llama 4, the subsequent model to Llama 3 that I just talked about, on a scale of 100K or larger. So in some sense, now the scale of these clusters is hundreds of thousands of GPUs, and we have quite a lot of insights coming from operating these clusters over the past 5 to 6 years, and that's what we'll be talking about, right? So in terms of the evolution of the clusters, first we built really small clusters because we were really concerned about Rocky's ability to scale to multiple hops. So we built single hop, clusters with just 128 GPUs each, about 50 of them, and then we were using them for specifically ranking and recommendation engines. And then in 2021 to 2023, these ranking clusters became, we started building multi-hop, 2-hop clusters with a 4,000 GPU scale of a cluster size each. And this is because the number of product groups at Meta that started to pivot towards full synchronous training and GPU-based training increased, because the early adopters essentially saw great results in terms of the model convergence and accuracy of predictions and so on, right? So obviously when GenAI came along, so the first thing we could do is, like, we didn't have time to essentially, excuse me. Oh, Chrome crashed. Give me 1 second. So yes, so when Gen AI explosion happened, and when we wanted to train Llama, in our production network or production infrastructure, the first thing we could think of was reusing the existing ranking zones to train these models. So we did that in 2023. But then over time, as we talked about, the need for larger and larger models, was very evident, and hence we started building 24K clusters, and then a cluster that's larger than 100K scale, and so on, right? Although there's a lot of innovation and scaling happening on the Gen AI front, we still continue to deploy ranking clusters, which are a bread and butter use case, right? And in terms of the software stack, that's about the hardware and the cluster sizes. In terms of software stack, this is a pretty well advertised picture, that the software stack of training involves the workloads themselves, the model code itself, the PyTorch, or basically an ML framework, which has compute component, but also has a distributed component like this PyTorch distributed, and then a collective communication library below it, and a transport interface like CUDA or IB verbs below it, and supported by hardware, which is a GPU and NIC in terms of the data path, and then the CPU in terms of the control path, right? So our fundamental principle in terms of like overall network and communication scaling and optimization, and overall, how we build for reliability, is to treat this interface of collective communication library and the transport interface as a very critical piece together in co-design between both of those layers, as to think about, instead of thinking about the transport interface as a predominant abstraction, where we kind of how we measure network efficiency or so, right? So that's served us quite well. We've been able to essentially move up the stack a little bit more, and being able to make the traffic patterns more friendly to the networks that we've built, as well as the transport we've configured, and thereby achieved really good communications efficiency for these training models. And in terms of of course, those are the direct interactions of software stack. We've also done quite a lot of work on the network stack itself, on the routing and the topology front. Especially on the topology front, we'll do a lot of work even prior to building clusters to make sure that some of the models of the models themselves or the workloads, we take them and make sure that we are able to build a fabric layout or network interconnect that can essentially support the upcoming or emerging models, that is like future llama generations or future recommendation models, quite well, right? We've also done quite a lot of work with scheduler to build network topology awareness into it, so that the job is scheduled in a way where it's conducive to our topologies and so on. So in some sense, we do a fair amount of core design to be able to operate these clusters in an efficient manner. There are two fundamental principles in terms of how we build our networks. The first fundamental principle is that we've always maximized the amount of RDMA throughput or scale out throughput that's coming out of the server. Certain operators, have, especially Asian hyperscalers, have chosen to, for example, go with fewer amount of RDMA NICs relative to GPUs, lesser throughput, maybe 1:2 or so, right? But we've always maximized the amount of throughput for scale out throughput that GPUs needed to get out of. And the reason is quite simple. I briefly talked about it. Our models in general have at least, especially the recommendation models, have a fair amount of exposed communication where the compute's not doing anything. So by not building and not maximizing the amount of network throughput or NIC throughput in the server, we would be essentially blocking training from happening fast enough, and we would leave the GPUs idle for longer times, essentially, right? And the second fundamental principle is that we've separated the backend and front end network right from the start, all the way in 2020 when we started building these networks. We just saw the trend or the writing on the wall that the GPU to GPU communication demand is growing at a much faster rate as opposed to the checkpoint or ingest traffic rate. And for that reason, we separated these networks distinctly, and they've been growing in their own trajectory, if you will, right? In terms of the overall solution, which involves network topology, we predominantly used multi-layer class, and we continue to extend it in order to build bigger and bigger clusters. So the 24K scale cluster that we had built, that was a 3-layer flow or so. And as we're building larger and larger clusters, at larger than 100K scale, we take several instances of such 3-layer class flow, and we mesh them essentially, right? And in terms of routing, we've explored several routing solutions. Started with static routing because ECMP was not going to be scalable because training jobs produce collective patterns that don't have enough outstanding network entropy. But obviously, static routing did not scale. It was a very naive solution in the beginning. But we then invested in fair amount of multiple routing solutions in some sense, including some ECMP, some modifications in the collective communications library in order to increase the amount of entropy produced by these workloads, as well as traffic engineering and so on. We also continue to explore flowlets in this case, right? And in terms of congestion control, we initially started with DCQCN, which involves essentially ECN marking on top of using PFC to make sure we have lossless networks. But nevertheless, we didn't see great benefits with that. And there was also some bugs as we moved in the PCQCN implementation, or change in the way it was implemented as we moved to 400 gig. And that pushed us to actually depend on collective library itself directly to limit congestion. In terms of operations and perf tuning, definitely we've invested a lot in collective communications library, as well as on the network stack themselves, like switches, basically switch SDK, and reprogramming the switch SDKs to get the reliability, the observability, and the performance efficiency that we want. Okay. So In terms of one of the learnings that shaped our topologies, the first part is about how ranking models as well as like content understanding or generative AI models differ, right? So ranking models are still in the scale of hundreds of GPUs. Content understanding and generative AI models specifically also sorry not also but generative AI models are at the scale of tens of thousands of GPUs already, right? So this scale is definitely different in both cases. So the clusters that we build for both of these use cases, in terms of how they would look like, would also be different. Apart from that, the model and the data parallelism involved in the ranking models are different than those involved in Gen AI models, right? So, for example, the recommendation models have data parallelism. The embedding exchange, or a full mesh traffic pattern that's produced by embedding exchange, meaning all the processes need to exchange some amount of data to all the processes involved there, right? Recommendation models also have data parallelism, but that can be hidden or overlap with compute. So the significant impact of recommendation models in terms of what the network needs to deliver is you know it needs to be able to support this full mesh exchange of all processes exchanging data with all these processes. And the sizes are large enough that such exchange is actually bandwidth dominant, producing congestion and so on, right? So now if you go to generative AI models, on the other hand, they use, at least today, fully sharded data parallelism and classical data parallelism as well as pipeline parallelism, right, which would produce collectives like all gather, reduce scatter, and send receive, and many of them can be partially overlapped, right? So overall, though, these collectives produced hierarchical pattern, unlike full mesh traffic patterns produced by recommendation models, right? So we use this understanding as we build clusters in some sense, right? So the first, the AI zone, as we refer to it, it's a building block for ranking workloads. It advertises full bisection bandwidth, in between roughly a 4,000 GPU scale or so. And it's formed by taking 256 racks of 16 GPUs each in a CLO-like topology, where each of the top of the rack switch or RDMA, top of the rack RDMA switch is connected to 18 CTSWs and so on. So in some sense, 18 CTSWs connecting roughly 256 racks with one top of the rack switch each, forming 4,000 GPUs, right? Apart from this, we also made a choice in the beginning to use these spine switches with deeper buffers, so that if there is some burstiness in this traffic, which many of the collectives do produce this such burstiness, they can absorb such deeper buffers. And one of the reasons we did that was because there's a lot of literature about how Rocky cannot scale well with head of line blocking and so on. If you have a slow GPU or a slow server, it would persistently push back on the network, producing back pressure that would have to propagate all the way to the source, and in the way it would also slow down other flows that were not necessarily involved in the job at all, right? So that was the concern. For that reason, we went with deeper buffer switches, and that served us fairly well. And in this building block, we talked about this building block is offering full bisection bandwidth at 4,000 GPUs, but that scale is not enough for Gen AI, right? So we need a much larger scale. In order to do that, we print 8 of these clusters. For example, for the 24K cluster that we recently built, 8 of these 4K clusters, but we only populate 3K of them, 3K in each AI zone, and for power considerations. And we basically build another layer of aggregate training switches, which would connect these 8 AI zones together. At this layer, however, we have 1:7 oversubscription, or 7:1 oversubscription, right? Meaning if all the GPUs on one AI zone are talking to all the GPUs in another AI zone, they would get only 1:7, or 1/7 of the bandwidth, right, of the injection bandwidth. And the reason this is okay is what we just talked about in terms of how, like, the generative AI models are sharded or distributed, right? We talked about how they produce collectives that can actually tolerate oversubscription, and hence this design works just fine for large GenAI models. In general, using Tor architecture and not end of the row architecture till now has given us an ability to actually train more reliably. If, for example, we have to do maintenances on top of the rack switches, or if we have a bad SSD on the top of the rack switch, we only lose 16 GPUs or so, and we can restart quickly with some spares or so, as opposed to end of the row architecture or um, uh, rail optimized architecture, which would have essentially resulted in a larger reliability event, right? Depending upon your pod size or your end of the row of this of pod size that the end of the row switches are connecting, you would basically have lesser reliability potentially in that design. However, we understand that end of the row design comes with lower latency and so on, right? So the way I would put it, and so as to why we stuck with the Tor architecture for the past 5 years, is that, of course, all of these models are latency sensitive, but they've not been, especially some of the training models that we've been training with, but they've not been training, as sensitive to latency within, 5 to 10 microseconds or single digit microsecond, scale. And so, this turned out to be an overall positive trade-off for us. However, as we talk about distributed inference, which is a future use case, definitely those models are running into traffic patterns that do get sensitive to a few microseconds, maybe low double digit or high single digit latency, right? Or in terms of microseconds. So in those cases, we may visit end of the row clusters or so, or end of the row topologies or rail optimized topologies or so. Yes, so I think that concludes the topology section. So in terms of load balancing, we did quite a lot of work, primarily driven by the fact that I'm just giving an example of 128 GPU collective. For 4 different collectives, in terms of the average number of Q pairs that they produce, active Q pairs that they produce in an instant, or the active amount of flows, you can see they're pretty small amount of flows, right? This is the reason why we couldn't use ECMP out of the box, back when we started with the first 2-hop network or so, right? So we started with static routing, as I talked about in our introduction, which basically, our networks divided into 16 prefixes, and what we tried, how we routed the traffic, especially egressing the RTSW or the top of the rack switch, is basically that, hey, if you're going to this specific destination prefix, take this particular uplink. And we wrote series of static rules. And in the case of fallback, we had an ECMP fallback mechanism and things like that. But nevertheless, that did not scale. And the reason for that is this very simple example of a job between server 1, server 2, server 3, and server 5, where server 1 and server 2 are talking to server 3 and server 5, but they're distributed between the lower 8 prefixes. And hence, with this very simplistic static routing schema, you would only use 8 of the uplinks between server 1 and server 2, which would result in roughly half the throughput that you can achieve, right? So once we ran into this issue very early on in our deployments, we invested in a couple of different directions. The first part is traffic engineering. Is based on the traffic demand that is observed in the first few minutes of the training job, and as well as some signals from the scheduler, so as to, hey, what are all the GPUs and all the NICs and prefixes that are involved in this job, and thereby we calculate the traffic matrix, and we use this traffic matrix and the network design itself and some signals from the scheduler, and we use a constrained shortest path first algorithm in order to generate demand and program routes on these switches, up until as long as the network topology is stable, right? If the network link goes down, for example, we fall back to ECMP for that traffic for a moment, and then once we learn about the new traffic pattern, then we go and reprogram these routes, right? So this worked fine in general, right? It improved our consistency in performance and the variability in our performance that we saw in the first stage of the network due to static routing issues and over time. And we did series of things in terms of how we rolled out these traffic engineering solution. But nevertheless, this worked out mainly fine for 2-hop networks. Once we moved to 3-hop or multi-hop networks, we definitely saw a fair amount of difficulty in terms of being able to scale this traffic engineering solution to multiple hops, right? There's a couple of different reasons for that. In general, more network hops, larger amount of endpoints and larger job sizes, meaning the complexity of the software solver in traffic engineering exploded. That's the first part. The second part is that we use multiple vendor switch, device switches in our spine network and even on the top of the rack. And especially in the spine network, different vendors essentially advertise different ways of like programming, routes and exact match entries and things like that. And managing all of that, managing the software complexity of the controller itself, evolving it along with the job sizes felt like quite tedious. And for that reason, we did not actually use traffic engineering for 3-hop clusters and so on. In those cases, definitely we went back to ECMP, but then we try to solve the fact that we have really few amount of flows by modifying the collective communications library so that it would produce a flow, a given flow with multiple work requests that I highlighted, four work requests in the first case. And it would either take each work request and split it amongst multiple queue pairs and post them on multiple queue pairs so that it would appear to the network as there are multiple flows. Or we also implemented a scheme where we took each work request and we send it on a different queue pair, and each work request goes and so on. Right. Both of these, mechanisms showcase like promise in different collective sizes and different traffic patterns. But nevertheless, for Gen AI traffic patterns that were produced, the second schema was turned out to be quite profound. Right. Um, so we used that second schema for training Llama 3, for example. And I had this example of like, the QPair scaling impact on all reduced performance if you're using regular good old ECMP hashing. You as you increase the amount of like QPairs, you see that the performance that we can get and the good put that you can get gets closer and closer to roofline, as expected. Right. You can also see a snapshot of the number of active flows that a generative AI job produces and ranking job produces. As I showcased earlier, for a job size of 128 GPU, we were just having like 10 to 15 flows at best or so from a given NIC perspective. But you can see that by employing QPair scaling, we've been able to increase the number of active QPairs to a fair amount. In terms of in some cases thousands, or in the case of generative AI, hundreds or so. Right. So I think the last aspect that I'd like to talk about today is basically the variable amount of, even after fixing the load balancing problems, the congestion produced by collectives, or the amount of buffering, in the leaf switch or in the top of the rack or switch or RTSW is non-trivial. In this snapshot, it's cumulative of all of the ports of buffering, but nevertheless, in terms of the loaded latency that it contributes to such buffer buildup, it's non-trivial compared to the unloaded latency of the topology itself. Right. For this reason, we need some kind of way to manage and limit this congestion, especially as we go to larger and larger scales and more complex traffic patterns. Right. So the beginning, we started with DCQCN, as I talked about in our introduction, and in general, the way I would put is that DCQCN turned out to be a non-net positive outcome in terms of turning on DCQCN. We were able to, yes, of course, get better buffer buildup, but sometimes in corner cases, we had to sacrifice performance, for such setting, for some collectives and some particular collective sizes, particular GPU gang sizes, and so on. Or we would kind of relax the DCQCN thresholds or ECN threshold, or react to them much more infrequently or rarely, or we would taper the response in terms of how we would react to the congestion events. And in that case, the buffer buildup would be fairly high anyways, or so, right? So in general, this did not provide us a net benefit. And the reason for this is essentially, I think, how we, at least this is the hypothesis, that it depends on this aspect of this observation is because of how collective communications library architecture itself, right? Collective communications library architecture uses two-stage copy and two-sided communication. Specifically talking about two-sided communication, what it refers to is that the CPU proxy that's managing, for example, the control path for on the sender and the receiver, in terms of if you take a single flow or single exchange between a sender and receiver, the CPU proxy on the receiver needs to actually tell the CPU proxy on the sender by posting a small message, which is like hundreds of bytes, by telling what exact data that the sender needs to send to the receiver, right? This signal is called as clear to send, right? So only when a receiver sends this clear to send signal to the sender can the sender send this data. But because of this two-stage copy architecture of the collective communications library, the sender cannot post a RDMA work request from sender's compute buffer to the receiver's compute buffer directly, right? Instead, it uses a channel buffer or an interim buffer in order to buffer these transfers going from sender to receiver, right? And the overall amount of outstanding data with the RDMA work request depends on the size of the channel buffer, right? So if the channel buffer size is very large, then you send too much data, you post too much data on the RDMA NIC, which ends up on the network. Depending upon the traffic pattern, that can cause congestion. If you size the channel size, if you set the size of the channel buffer to be too small, then essentially you're undersubscribing the network and you're not getting enough performance out of the network, and so on. So once this RDMA transaction happens from one channel buffer to another channel buffer, which ultimately makes it to receiver's compute buffer, right? As the RDMA requests and packets are going through, for the work requests are going through, and you're getting acknowledgement packets back, and the sender essentially uses these ACK packets and signals from the receiver to sense a completion event, right? So if you look at this, how we use this architecture in order to essentially deal with congestion, limiting congestion, is that we took the size of the channel buffer on a per collective basis and tuned and wrote a static tuner essentially that would go and figure out the size of these channel buffers to be optimal enough that they're not causing too much buffering, but at the same time they're not under subscribing the network, right? And this helped us limit the amount of buffering on the network for sure. Combined with this fact and the fact that we use debuffer switches in the spine, we were able to deal with congestion overall and the bursts produced by various collective patterns overall, right? So yeah, I think so I'm going to skip a few of these slides. In general, I think what I was trying to showcase here, that distributed inference, which is very emerging, is becoming more and more common. And distributed inference has two parts: prefill and decode. And in the case of prefill, you could also distribute it between various servers, and decode, also you can distribute it between few servers. And decode parallelization specifically produces really small messages, for some of our models in the scale of hundreds of kilobytes, and hence the overall latency offered by the network is starting to become more and more critical, especially for distributed inference, right? So yeah, with that said, I think in terms of what's next, right, bigger models, more GPUs, longer distances, and at longer distances, can we still essentially maintain losslessness, or do we need lossless transport? Larger scale up domains, for example, the NVLink 72 domain that's coming through, that starts to play a really, really important role in the overall communication. And as I just talked about model serving, it's producing really small amount of really small message sizes, which is a very unique and interesting challenge in terms of how do we kind of create topologies that have, it's like rail optimized topologies or end-of-row topologies that offer really low latency, but nevertheless, can you use that infrastructure fungibly for also large gang training, which requires really a high amount of reliability? And in that case, how do you manage this, trade-off between reliability and performance, right? Yeah. With that said, I think take questions.
We've got one question from someone online in general. How is GPU full sync training different from GPU sync in the gradients for every iteration on forward backstore propagation?
Can you repeat the question, Jeff? So how is GPU
full sync different from GPU sync in the gradients for every iteration?
Yeah, I think so. There's a couple of different training modalities, right? There's full sync training where you essentially synchronize every every iteration between all of the GPUs. You can also do, in some sense, the other extreme of this is that you don't necessarily do synchronous training, right? There are different processes doing their work, and they report back their progress or their gradients in some sense to a parameter server, and the parameter server essentially, as those things are coming along, essentially does calculations and lets the processes know in terms of the synchronized output, like an all reduce or so, right? That is the other extreme, right? And then there is something in between in terms of like, hey, instead of synchronizing every few training iterations, every training iterations, can you synchronize every few training iterations? You're still synchronous, but you're doing this, at different amount of like iterations, right? I don't know if that answers the question.
Next question is, what exactly do you mean by longer distances? Do you mean
Yeah.
DCI, same metro between metros, and so on?
Yeah. So like, is the question about, like, I guess, specific, what is a longer distance, right? Like, it's sort of a very relative term in some sense, right? So longer distance specifically, I'm talking about is that we are approaching scales where a single building or a single region amount of power that we have gets limits the size of the job of training that we can do in some sense, right? And for this reason, because the limitations of power and all the supporting services you have to accommodate in that region in order to continue training, you may have to go to training a job between distances of tens or hundreds of kilometers between them, right? So this is what I refer to, and the previous question in some sense is related to this, right? That a full sync training, can it still scale at these larger distances, at tens of kilometers, maybe, I think, but in hundreds of kilometers, will it still scale, right? If it doesn't, then do we go to partial sync training, or do we go to full async training, right? And how does that look like, right? And then at such scale, are there like homogeneous topologies, or they're heterogeneous topologies, right? Heterogeneous compute. In that sense, like, how do you divide the work between them, right? So those are the kinds of, I think, interesting challenges that are coming along. Yeah. Any other questions?
Adi, thanks so much for taking the time to talk to us, and really appreciate it.
Of course. Thank you.
And looking forward to your future
Absolutely.
participation in AITF. We are going to move to next presentation. Peter.
Hey guys. Hey Jeff. Can you hear me?
Yes.
Yeah, can hear you.
Hey, Adi is the first one to respond. Give me a second. I'll try to share a presentation. You never know how it goes. First of all, while I'm trying to do it, let me try to, goodness, advanced file. Actually, I can't seem to share the screen anymore. Jeff, is it expected? Give me a second.
At the bottom of your screen, there is a share button. Do you see that?
I click it. It only shows, okay, show me WebEx application. Oh, it's on the screen. Okay, not the app. Well, there it goes. Let me see if I can share the screen entirely. Can you guys see it?
Yeah, it's coming up.
Yes.
Good. Okay. Well, hope nothing comes across. Looks good.
No, looks like not yet. You just shared your WebEx, not the presentation.
Plastic man. So you can see my screen, right?
I can see
give me a
the
second.
screen. Yeah.
Great. What about now?
It's good.
Oof. Okay, thank you. Thanks
Still
for
the
inviting
same.
me, Jeff. Wait, people say they can see my screen now.
Coming up. Yes, we see your
I
presentation.
wish I could say a few comments about the WebEx, but I'll skip that complaining part about video conferencing. So today, I'll continue the talk I gave in the previous IETF. The previous one, if you remember, maybe some of you remember, was about the fabric evolution from like 2010 to like modern times. What's common, what's uncommon. And this topic, today I have less time a bit, so I want to focus with one aspect of network design, which I find interesting. This is a choice of topological aspects, like using top-of-rack switches or real topologies. That's something Adi mentioned briefly in his talk as well. And that often is a topic of debate among people. So I thought it would be good to bring it up and highlight the challenges people try to address with these design choices. So the name of the talk is a pathetic pun at the, I think, old song from the 70s, I believe. But nonetheless, let's proceed. So today, I have 3 sections in this talk. The first one is about collectives and how they map on the network and what comes out of it. Then comparing briefly the top-of-rack and well-optimized topology choices. And then touching upon the so-called rail-only topologies, right? That's the name people use today most often. And Jeff, feel free to stop me and ask questions in the process, because all I see is my screen. So I'll just, power through as the slides go. So this
We will
slide.
hold the question till the presentation.
Okay, cool. This slide gives you a very simplified picture of HGX 800 node. That's what people deploy today. It's not the most, I think, up-to-date system, but that's what mostly commonly deployed. So probably the most important thing about the GPU server systems is that they have typically 8 GPUs. These days it's reference design. And then each GPU has a NIC attached to it, either directly or PCIe switch. Typically it's one PCIe switch shared across 2 GPUs. But this very important part that I mentioned in the previous talk, there's also a small NVLink fabric. There's a high-speed network which has a few switches inside on the board that allows these GPUs to talk to each other directly at pretty high bandwidth. Roughly speaking, the bandwidth of NVLink is 9 times x the bandwidth you have on the scale-out NIC, the NICs which you see on the sides. Of course, there's more components to it. There's actually a lot of components in the system. There's CPUs, typically 2 sockets in the system, PCIe switches, and so on. What's most important is that we have 8 GPUs, 8 NICs, and the switch. And this node, as we'll see, is act as the unit of traffic injection in the GPU networks. So this is a very good attempt to show how a collective traffic look like between 2 machines. Remember, I just mentioned that we have an NV switch, and that's the fact that Nickel library exploits a lot by implementing collectives logically flowing as a ring. And in fact, ring was the first collective they implemented in Nickel, mostly because ring topology logically is bandwidth efficient, right? Ring has no bottlenecks if you map it correctly on the topology. So in principle, you have no congestion. In principle, it's a board world. So here, notice that when we run traffic between the GPUs, let's say in this case, it's all-reduced collective. All-reduced means you have to sum up all the weights or average them, but we have to run this computation across all the GPUs. And here we exit through the same NIC as we enter in the system. So all this logical topology is built and maintained by Nickel. So it has to run this, of course, traffic over IP verbs connections, InfiniBand or Rocky, which is between the servers, and also inside the server using like Nickel channels for net Nickel. Well, Nickel channels and the link memory copies to transfer data across the GPUs. And also on every GPU, it's not shown, but there is a process that a kernel does reduction, gets the data, does reduction, and pushes it forward the pipe. So the most important thing is that nickel creates many of those rings, right? So in case of in case of O-reduce, the important property being that using this, you can now bundle all these nicks together to act as one gigantic traffic injector. So effectively, O-reduce would have capacity of 8 nicks to do reduction across the 2 GPU nodes. And I keep saying O-reduce, even though today it's less commonly seen in this in the training or well, mostly in training. In inference is still very common, but the pattern applies to our collectives as well, right? The most important part is I want to just remind you: we go in the link and we loop around and we exit through the NIC. And of course, you can use 3 topologies, logical topologies across the machines to implement collectives, but internally you still have the logical ring topology across the GPUs. So this is how things look logically, right? And then you want to understand, well, how does this flows map physically on the other topology? So here comes well, this recap. I always actually recapped it, so we can skip it. Here comes the part where you look at how this node with 8 GPUs and 8 NICs connects to the network, right? So below here at the bottom, we have a server with the same 8 NICs, and in a Tor style connectivity. I don't have a better name. I call it Tor style, even though it does have to be a top of rack switch. It could be end of row switch. But the important part is that all the NICs from a server connect to the same switch, right? You can call it the parallel cables go into the L1 switch. So when all these traffic rings exit the server, what's going to happen? They have to then next jump to the other switch above L1 typically, because they have to cross more like one server to the collective, right? If your traffic stays in L1 switch, you're fine, right? Maybe you have like 2 servers, 4 servers, and traffic doesn't cross the switch. But if you go above, you have to use the uplinks. And this is where it gets interesting, because now you have to load balance this collectives traffic across the uplinks. And remember, by default, it's only CMP, right? By default, of course, if you don't change anything. And now your rings may overlap, or trees, whatever you use. And once you overlap, you can lose bandwidth very, very quickly. Like contention on one link may cost you almost 50% performance on the collective, right? So this is why early on, people usually frowned upon top of rack configurations, because they thought that, well, tons of collisions, it's all bad for for your health and so on. So don't do it. And so from very early days, I think this came from HPC days a while ago. There was an idea that you can take the node, right, and you can fan out the links from the node, not only in parallel, but fan them out to multiple switches. Typically, they're called rails, even though this term is very heavily abused and overloaded, but we'll stick to it. Like here, we have 8 NICs per server, so we fan out 8 links and we put 8 switches together, right? As a result, you have now 8 rails. And the result is that the traffic leaving server 1 and going to server 2, all these logical rings, they can now stay on these L1 switches. They have to go above the rail switch level, which is nice if your collective entirely fits on these N servers. So here number N is the switch radix. So if you have a high radix switch, let's say, I don't know, 128 ports or something, you can say that about 64 by 8 GPUs can stay in one rail group, and all their comms remain unobstructed, right? You don't have to cross the uplinks and then figure out the contention on this links going above this first hop networking, which is actually very convenient, right? Very convenient because even if you somehow can figure out how to load balance things, it's nice not to worry about it, right? If you just compare this, right? I think I touched this briefly. On the left side, we have top of rack topology. On the right, we have rail connectivity. So top of rack has a switch in the rack, ideally, because this is nice. You can use copper cables, they're more reliable and cheaper. But you're limited by the volume of servers you can put in a rack and under one switch. So traffic has to often cross the link between top of rack and next layer switch on the left side. At the same time, with the array configuration, what's going to happen? You go across the rail switches. It's great, right? Your static stays local, your contention is minimized, and also if you care about it, right, you also have less latency because you only cross one hop switch, right? Like potentially this switch and top of rack config can be far away. Let's say, I don't know, like in different data hole, and it may cost you a few extra microseconds to cross. Not that it matters that much in most cases, but if you have very long rings, it does add up. Latency does add up as you cross it. So in many cases, people who build networks, they prefer rail design because it saves them some headaches, but it has additional trade-offs, right? The biggest gain, I imagine, at least from my thinking experience, is that top of rack would work fine for you if you figure out load balancing solution, right? Which means you have to have some good scheme for adaptive routing. And adaptive routing comes with its own set of headaches and trade-offs. If you do like flowless switching, you get packet reordering, you have support packet reordering beneath. I mean, it's not unsolvable, it's all done today, but it requires some tuning. I think Adi also mentioned before me that in most cases, you can just pump entropy. You know, people like this word entropy, create more flows, queue pairs, and eventually just have flows balanced like better across uplinks. So where you have your classical trade-off problem, like Gauss paradox, you still have collisions, but you have much less imbalance across the uplinks. So in many cases, simply pumping the entropy, creating more queue pairs works okay for top of rack switches. Not ideal, but you know, pretty well for many cases. And also rail configuration has one trade-off. Rail structure requires to have these domains, right? So your collector has to fit in this one domain, which means the job, when we schedule it, has to also map properly on this domain. Like if for some reason you decompose your parallelism such that you cross multiple rail domains, well, I mean, tough luck, you have to cross the next level of switching. So this gives you a bit more headache for scheduling, right? And top of rack is pretty much flat, you know, like it has one bandwidth pool, which is really nice, by the way. You don't have to worry about topological structure. So what else? Oh yes, Rails, actually one of my favorite topics. Rails require you to use optics to connect from the NIC to the switch. Why? Well, because you really want to cover more nodes from one switch, which means you have to put your switch somewhere mid-row, end of row, whatever you like. Maybe not a big deal, but potentially optics fail more often than copper. Not potential, actually, practically. It's pretty well known. So you would have more headache with failures. I mean, it depends on the scale, of course, and the optics and everything else, but even theoretically, it's a bit more headachy. The other more important problem, I think, is that real structure has this, notice here, larger domain, right? This R1 covers much more nodes. So if you have to do maintenance, like switch upgrade, software upgrade, you affect much more servers. It's not unsolvable. Like if you have multiple switches and multiple planes running out, you should be okay because you can take the capacity hit. But in the most basic scheme, you really are gonna take the whole domain down for a maintenance from a single switch, which could be also unpleasant. And the other one, I think, important but subtle, now that the switches are outside of a rack, you cannot do integration testing at the integrator side. You have to connect things together at the data center and test things there, like NICs, optics, switches, which is, I mean, more headachy. You have to do much more work in data center. It's really nice when you can do integration testing first before X ships to the data center, and it arrives to you with top of rack ready, you know, everything else. So this is very, very non-performance driven considerations, but they're all important, right? Otherwise, I think rail configuration is almost no-brainer, right? You save hops, you save traffic, it's all nice and great, but there's this practicality trade-offs which add up, and it's something to consider. So So realistically speaking, right, if you have this real structure with fan out from the server, you may need to talk across the ranks. Like say in this case, we want to talk between the red and green NIC, right, on different servers. I mean, like you're out of luck because you have to go above the rail. People often call it the bridge, right, the bridge layer. I mean, in reality, it's same cross topology, but with different fan out, but you have to somehow cross the rails. Now, this may not happen, but this is a necessity if you want to cross the rails. The other way, which is very NVIDIA specific, right, because you have NV switch, you can cross the rails using the NVLink switch, right? In some sense, people often don't think about this way, but NV switches, they're kind of top-of-rack devices, right? Except they are hidden. It's like a mini top-of-rack switches which can serve as a transit devices for the GPUs. And this is a feature known as PXN in nickel, right? It allows you to do send receive pattern or even other collectives across NVLink. And that is actually pretty efficient, right? Depends on your situation. But this need often arises in the collectives which are not rail aligned, like actually all-to-all or send receive, because they have to go and let every NIC or every GPU that you have a GPU. Like this pattern is very common in training the recommenders. We have to do lookups in the embedding tables. So we have like these two methods to cross the rails, right? But then of course there's this interesting like idea. Well, if my collectives are always rail aligned, if my job is placed such that rails are always available for collectives, maybe I don't have to cross them. But obviously, as I said sarcastically in the first line, it depends on application. Like for example, in recommenders, you have to cross rails because you have to do table lookups, right? Embedding tables. But for transformers, in most cases, actually almost every case, you split models such that you're always rail aligned, pretty much, if you place job properly. You have tensor parallelism, which is typically per rail, and when everything else goes from there, you have reduced scatter, old gather, which are rail aligned. You have maybe pipeline, which is actually not, it's actually still rail aligned properly. So you may just say, like pretty much everything is contained under rails. So I don't have to have a cross fan, right? And then people say, like seems like it's pretty nice if everything is like sliced in these end planes or end rails, whatever you call it. Maybe I don't even have to have this extra bridge. Like maybe I don't have to use PXN or have this extra bridge. And this gives this idea, which is very commonly incurred, when we just like do rail-only topology. So we do only one hop network, which sounds cool, right? In theory, you connect servers using, in this case, 8 rails, because you don't really have only 8 GPUs, 8 rails per server, and you use switch of maximum radix. In this case, I use example of 512 by 100G, which is, becoming a common in the industry these days. It's one ASIC still, but you can probably find a bigger box if you want. Not that it's a good idea necessarily, but you can build a very large fabric, not say very large, relatively large fabric for many cases, which in this case, let's say 4K GPUs, but only one layer of switches. And in principle, you can also even theorize, what if NVLink domain is actually bigger beyond 8 GPUs, can I build even larger rail-only topology? And the answer is you can in principle, but should you in practice? It's a big question, right? Like this schema right here on topology would work, right? If all your collectives are rail aligned, things will work fine, right? And for point-to-point, you can use PXN to cross the rails across the servers, but even that is not necessary because you may not need to have to do that. But of course, the question is, well, okay, this is great. Should I do it or not? And of course, there's a very, very nice property that you don't have to worry about load balancing, right? Or adaptive routing or anything else, because you only have one hop switches and everything else happens in the fabric inside the switch, which hopefully works well. And of course, you cut this extra of switches, so you save some power and dollars on the optics and switches. And you can always brag to your friends about rail topology because it looks cool on diagrams. But unfortunately, it has a trade-offs as well, obviously. First of all, you have limits of scale, right? If you want to build 100K cluster, you probably won't do that because you simply have not enough radix in a one hop switch to build this topology. Obviously, maintenance radius is pretty high. Like, look here, right? You take one switch down, you affect like 500 servers, which is pretty bad, and people will not like it. I'm pretty sure. As I mentioned, there are ways to overcome it. Like in this case, since you can split this, say DR4 optic cable into 4 parallel planes, so you may have actually additional switches like planes, and you can decrease the impact of maintenance. But that requires that your NIC supports, proper load balancing across multiple lanes, which is also tricky. Not impossible, but tricky. And I think there's another sad fact is that you can't really use copper. I mean, I've been thinking that copper would die by now, but it's still alive and kicking. So I gave up. I think it's pretty reliable technology and works pretty well. And the fit for a copper was 1, right? It falls once in a Brazilian years. So it's pretty good for reliability. But most important, I think, in my opinion, architecturally, this design depends very heavily on your ability to map application on these rails and cross the rails somehow, right? And to scale it, let's say, look at Grace Blackwell. Grace Blackwell is 70 GPUs enabling domain, but you cannot do PXN there because PXN requires you to do signal in a shared memory across the proxy threads. It's not impossible to signal across the different nodes in the enabling domain. It's not supported right now, and it's also not very efficient because you have to do some of the IPC across the nodes. So as you scale bigger and bigger, this idea gets more and more fragile. So in general, I think there are limits to these designs, in my opinion, which usually are fine for smaller clusters because you can really do it really nice and neat. Assume you can tolerate this the implication of maintenance impact of a single switch, right? But in general, you probably have to find a design for your needs, which probably doesn't use rail-only topology and has some level of bridging across them, because it's always safe to have it. And it does cost money, of course, but compared to the cost of infrastructure, it's probably worth to do anyways, just to have that safety and save some sanity on debugging all these rail-only issues. But just my take, right? Of course, people always do some fun stuff wherever they can, and I think it's always good to try new ideas. So this is it, Jeff. I think this concludes my presentation. It was short this time, but I'm going to take any questions you guys have.
You need to.
So here's a correction because I felt the same thing when I was presenting it. The NIC is 50 gigabit. The NVLink is 500 gigabyte when you go back up to 2 tera. So the bandwidth asymmetry between the NIC and NVLink is actually 10x when I was also thinking.
It's 9x.
Oh,
no,
9x
it's 50
roughly, yeah.
gigabit and 500 gigabyte on the NVLink.
It's 4 gigabit NIC. The difference is 9 times.
I'm happy to argue about speeds and feeds, though.
Gigabyte.
It's my favorite topic. Yeah, I think, sorry, the question is if it's HGX and H100, so CX7 NIC, for example, is 400 gigabits, which is 50 gigabytes. And I apologize, I know, but every time I put gigabyte per second, B capital, people get upset because it's confusing. People think it's actually gigabit per second. I apologize. It's a very well-known confusion that often comes up. But when you talk to people doing GPUs, they all measure things in gigabytes per second or terabytes per second. So I made this mistake in the slide.
Any more questions? Go ahead.
So one quick question. In multi-tenant scenario, do you think the solution is also high efficiency?
Oh, that's a very good one. I think Mazi may remember we had the same question when we were thinking about these clusters at Meta. Like, well, if you do Rails, you have to align your tenants on the Rail boundaries, so it gets more headachy. It's totally doable. I think it's doable because mostly about the average job size, and usually most of the jobs for training are small in the cloud. People don't train gigantic as jobs there. So if you can bin pack them to staying at the Rail boundaries, you're fine. But sometimes this also may cause fragmentation. Like your job, I have to straddle, the Rail domains, and then you have to kind of put it on one side or another, and this makes some fragmentation. But in general, it depends on the job size average. And typically, as I said, people use a lot of small jobs, so you can always bin packet efficiently. So there's no big difference, I think. The biggest impact, as I said, probably maintenance, right? When you have to take down a node and affect the whole leaf group, which is seriously disrupting for people.
Thank you.
Of course.
Any more questions? Someone online? Goes one, twice. Peter, thanks so much for taking the time. Really appreciate it. And
hey,
we hope to see you next
course, Jeff.
week.
Thanks for inviting me.
Providing more.
Thanks for listening. Sorry for the rambling. Thanks, folks.
Yeah, so thank you. We are going to bring JK. As for Nickel specifics, every year there's a yearly event at NVIDIA called GTC. I highly advise you to use for Nickel presentations. This is where PXN is introduced. I believe it's 3 years ago. So there's a presentation every year talking about Nickel, specifically how it uses PXN to provide and building communication between servers. So please do take a look. It's really interesting. And JK, we are bringing you in.
Good morning, good evening. Thank you for having me. Can you guys see me in my screen?
Yeah, we can see your slides. We can hear you.
Thank you. Perfect. Yeah, thanks again for having me here. Just as a disclaimer, this is my first public presentation since I joined Google. I joined Google last year. I've been working on AI, data center networking. So this is a great opportunity for me to share a little bit of direction that we are going in. So I checked the contents of the today's and also prior AIDC forum presentations. Great materials talking a lot about routing, topology design, and then scale and load balancing. I'm not going to talk about any of them to some degree. It is more about physical design and deployment. Since we are all rushing into increase the performance at scale, the bandwidth and latency, which pushes the scale out. And that means that large amount of networking gears we have to deploy and manage, right? And when we do that, we have to also honor the constraints in the physical world and data center, power, space, etc. And then at the same time, GPUs are expensive and TPUs are expensive. All of them are very expensive. And there are huge amount of demands coming in. So speeding up the deployment at scale is another kind of very interesting question and task for us. So we have to design network in a way such that we can deliver and manage the network, large scale network at scale at fast. So here again, I'm not going to share any particular solutions, but wanted to share a little bit of the design goals and requirements, and want to also hear from the community here. And many of these points, the focus is mostly on in the data center, the building level data center networks, but many of the points can be applied to either campus or metro or wider area interconnect. So yes, we are all rushing to deliver performance at scale, and then performance in two different angles, right? Bandwidth and latency. We know that the per accelerator, either GPU, TPU, the bandwidth demand increases really fast every year or every other year. And then at the same time, thanks to technologies like liquid cooling, the per rack density of those accelerators also increase. So the combination of these two, meaning that the bandwidth that coming out of or needed by the per accelerator rack, machine rack, increases multiplicatively. At the same time, I think everyone knows that the scaling law of LLM continues. And we are talking about now hundreds of thousands of accelerators in one training job and cluster. As discussed a lot, we also want to deliver the bandwidth with also latency in mind, because the collective performance is quite sensitive to latency and then the flow and hash collisions happening in the fabric. So as a result, we want to pack as many chips, accelerators as possible under the small hop distances and fiber run length, so that we can deliver the performance and bandwidth at a low latency. So what does it mean to actual physical design and deployment? While the multiplicative bandwidth increase, the bandwidth per machine rack demand increases, is there. At the same time, your networking speed also has been going up way faster than now the CPU speed. But at the same time, the surge speed increase is still linear. It's not really super linear. So as a result, we are now seeing more number of network racks, fabric racks we have to deploy to provide the bandwidth, provision the bandwidth needed by the machine racks. And then the speed is higher than the number of machine racks we have to deploy. So deploying the machine racks, the fabric rack themselves is becoming a bottleneck, can be a bottleneck. And we have to also connect the machine racks and the network racks, all the racks across different layers through optics or whatever fiber bundle system. And the number of fibers also increase. And I also learned that just not deploying the fiber bundles in the DC layout, but also connecting them each other. There's no such automation done. So it's all manual work, very error prone, and that the volume also increases fast. When we talked about latency, what does it mean? That means that very dense logical topology, maximal fan out as much as possible, as also Peter presented in the previous presentation, nice diagrams. And that means that we also need to deploy just a dense logical topology into dense physical constraints and space with other constraints, like some fibers has to be covered up with a secure conduit if they have to cross different rooms, data halls, or data centers. And we also need to provide enough path diversity for the physical path diversity, not the logical routing path diversity for the fibers, because at rare case, if one of the conduits are damaged, then we don't want to lose the entire, expensive AI data center. So there must be physical diversity of these fibers being laid out across the data center. And also power and cooling infrastructure complicates with the liquid cooling, etc. So I don't think I need to repeat this one, but yeah, these are all combined poses pretty good amount of challenges for us to lay out and plan and land actual racks and fibers at scale. Okay. Then how can you speed up the deployment? These are very well known, maybe common, maybe wisdoms. Some of them are more detailed in the paper below, and published at HotNet 2027 last year by Jeff Moore and John Riggs from Google. Some high-level bits I can think about and internalize myself was starting from the rack design. Let's use common rack as much as possible across different layers. Now, when you look at the the leaf layer, spine layer, super spines, they may have a different needs. But if we can actually make the rack design as common as possible, that helps us to reduce the complexity around the rack manufacturing, design, and then deployment. And for example, when there is any hiccup in terms of the supply chain issue, then common rack design also helps us to flexibly place the racks across different layers as much as possible. And fiber design, it's all about manual porting work. How much we can minimize the manual connection work. The porting meaning that connecting the fiber connectors from this patch panel or switches here and there, and as actually DC floor. So in many cases, the racks are built somewhere else, and then we get them shipped in, and then we deploy them and connect. So as much as we can left shift some of the porting work to the other rack builders, etc., then that also saves us time for our technicians to spend in actual DC floor. And when we also deploy different racks and then fibers in different sections of data center, we also need to optimize the space-time workflow of the technicians and equipment, because they have to move around, they need some space to work together, and etc. Another interesting aspect is the fourth bullet point here. We are all running around the clock, and sometimes the data center infrastructure itself may not be fully built. So we may have to start deploying the network gears while the other data center infrastructure like power and cooling is being set up. So we sometimes need to incrementally deploy network, not only for the need for logical topology construction and then bandwidth guarantee for the set of machine racks we want to provision as soon as possible, but at the same time, it has to be aligned with the other part of this infrastructure build steps. And again, there are many hiccups we can see. So it's always good to have some flexibility in the topology design itself, and then also flexibility around the deployment, so that we can handle the different hiccups around the mismatch between the demand requirement changes and the supply chains. And also very detailed in the paper, we talk a lot about simulations, right? Simulations for flow level, packet level, or job level simulations to better understand the performance of the LLM in interaction with the network. But there are different type of software simulations are very important, as I understand, which is physical world simulations, so that we can pre-test and left shift many of the testing of this deployment and the management workflow in software before we actually hit any issues in the floor, which will be very expensive to debug. Okay. If I can move on. Yeah, resiliency, it's handling the failures or the need for maintenance at scale is, I think many audience here may nodding on to the need. And at high level, this is very expensive fabric. We don't want any kind of network failures leading to kind of job crash and forcing the job to roll back to checkpoint, or even slow down the job. Either way, we want to avoid them as much as possible. That means starting from something like a proactive link monitoring and then qualification at scale. And also to help that, it's very good to have, or maybe critical to have, some clear signal telling, for example, whether this is actual failure or just momentary flapping in case of links. And it also is good to know, very useful to know when link is up, and clearly knowing that, oh, it's up, it's not actually flapping back. And having such a clarity all helps. And in case of failures, or maybe unplanned failures, for example, then the nature of the fabric is also quite matters. You know, if the failure somehow propagates, you know, that's the worst case. So we try to keep the fabric in a fail static mode, either data plane failure or our control plane failure, because we are heavily using SDN. That property combined with host-driven reactions like Derodex, you know, path migration when each connection sees some performance degradation or failure in the particular connection, just changing the hash so that you can explore different part of the network. And combination of these two works pretty well in our experiences. And obviously, it's well known that we want to align the failure domains across different areas like NVLink switch from the rack machine, and many failure domains are there. Power infrastructure and not only failure domains of them, but also maintenance windows. It's good to align them as much as possible. And in terms of handling the failures, yes, we definitely want to repair critical part of the network as fast as possible. For example, typically the leaf and spine, the link between them, you know, we have lots of redundancy. So of course we want to fix them as much as possible, but you know, the impact on the link down between a NIC or machine to the leaf switch or Tor switch has a more direct impact on the job. So it's better to actually increase the SLO on the links. But also, it's also very important to fail fast. Whether this is, so flapping is another good example, or any software issues. If you see any signal, actually it's better to fail fast, and so that especially in case of the large LLM, because any slowdown, an entire job slows down as at the speed of the slowest link or node in the cluster. So failing fast also helps. At the end, coordinating these multiple aspects, you know, repair, maintenance, monitoring, and in a way such that we don't really negatively impact the job performance, requires really good end-to-end coordination between many subsystems, network monitoring, management, and also job and application schedulers. So I believe there are many efforts going on in different companies and then vendor companies, communities, and it'd be great if we can share some of the insights in these kind of forums. Last but not least, you know, managing those large-scale systems, whether it's network or not, starts from telemetry. So I'm going to just start with maybe very obvious insight that there's no one-size-fits-all telemetry for different type of use cases. So there are heavy conversation going on. What's the best telemetry for congestion control and then transport? We have sometimes RTT, ECN, and maybe INT or CSIC, the one of the newest in IETF. Also, there's a need for performance monitoring and optimization. That doesn't necessarily mean the telemetry always just coming from the end host. We may need some telemetry coming from the applications and the end host, NIC, and also fabric switches. We need to see the telemetry signals as a whole. But at the same time, when we see incidents meaning that not just a single link or switch failure, but the type of failure that impacts the large job and then visible to the customer. In Google, we have a terminology like OMG, and triaging them as fast as possible and then troubleshooting is very important, because let's say if the cluster is idling, some part of the cluster idling for hours, days, we want to minimize the time as short as possible. So my high level understanding so far is that myself some of us worked on something like INT for many years, and the first top two telemetry needs, like congestion control and the performance monitoring, needs really good top-down and the system-level holistic approach, also involving lots of host and application-driven metrics. But at the same time, the third one, the triaging and troubleshooting, may really need more bottom-up approach, and the low-level metrics and is critical for speed triaging. And then how do we define the metrics is the very good, interesting starting point. We want to know what happened, whether it's a drop or a different type of event, and where it happens. Is a top of rack switch or an ingress egress, and when it happens, so that we can do better correlation if there are multiple signals happening in different locations, and why it happened. For example, when drop happens, is it because of the MTU or TTL or policy or congestion drops? There are many different reasons for drops if you talk about just drop as an example. And we found that who, meaning that which particular 5 tuple flow is culprit or a victim, is relatively less critical compared to the other 4 aspects when we talk about actually the incident triaging and troubleshooting. And these solutions better be lightweight, and so that we can rely on its existence on different software and hardware platforms. Okay, so this is my last slide. I have one summary, just saying that S-Care AI data center deployment and operation is critical so that we can deliver the bandwidth and latency performance in time or so. And designing not only fabric, especially the physical design, rack and fiber matters in terms of speedy deployment and operation, but sometimes it has implication on the logical design. And we see the lots of software issues actually, not only hardware failures, but software failures and upgrades are very critical, and we need good operation policy to handle them. At the same time, we may need a software system to automate the deployment operations. And I'm happy to be able to talk about this to some degree in this AIDC forum, so that we can share the pain points and ideas. And it'd be great if we can do some more collaboration. For example, starting from how we a little bit more standardize the telemetry metrics from the switches and NICs across the different vendors and ecosystem, and how we stream the interface telemetry information out of the devices. There is some work done by my colleagues in Google and other folks in OCP forum, like a GMPSI. I think these are another good examples of possible collaboration opportunities. I will stop here and happy to take questions.
Question for JK. JK, thank you so much for your time.
No
And,
problem.
we're looking forward to see you progress in your journey in building networks.
Okay, thank you very much.
I think there are people on the chat. Are you trying? I see a raised hand.
No, that was an accident.
Okay.
Sorry.
Okay, so I will share the information about how to subscribe to the AIDC mailing list in the chat window, and also the link to the GitHub repository. For this meeting, we don't have the slides in the repository yet, but we will upload them after the meeting.
So practically, we envision this meeting as a platform collaboration and educational for many people, because networking is a new discipline. So we are looking forward to your suggestions, your comments, and potentially sharing your own experiences. Many of us are working on AI networking as we speak. In the comments, I think there's a number of interesting points we'll try to address in the future meetings. One of them is, for the first time in last probably 5-6 years, we are moving from architecture with 8 GPUs or 8 NICs per server to larger scale-up networks. So NVLink 72, announced by NVIDIA, is going to be the first representation of that. It's the first rack scale architecture. It has 72 GPUs in it. They are going to be larger system, potentially up to half. 5. Yeah. 200, 200 killed that, but. So there are larger systems coming up. They will potentially change architecture, networking architecture, how we interconnect the system. So I think it's very important to address and talk about. Number 2 is longer distances. So as data center, as number of GPUs required per data center is growing and power consumption is growing, it's kind of becoming obvious that there's just not power and space to put all the GPUs single data center. So we are seeing training done over a longer and longer distances. That's pretty new discipline. Again, it's first year we are observing this. So talking about characteristics of training done over distances, I think it's really interesting topic, especially for IETF, because this is what we do, right? So that's another topic for discussion. And again, we are looking forward to your suggestion. Please do subscribe. And we'll see you next ATF. Thank you for being here. And thank you for all the presenters, of course.